Hello everyone, my name is Maisa, and I will present the paper Fundus Eye Image Classification Interpretation for Glaucoma Diagnostics. This work was done together with my advisor, Rafael. Here are the topics of this presentation: the introduction of the work, the proposals, the methodology used, the results, and the conclusion. Glaucoma is a disease that affects the area of the optical disc. It is a progressive disease, and the most serious stage causes total loss of vision. Early diagnostic is important to prevent the disease from reaching the most advanced stage, bringing a better quality of life for the patient. The diagnostic is made from medical images, like as fundal images, where the doctor performs analysis. This diagnostic is a challenging process that involves many specialists. With the advances in the area of the machine learning for computer vision tasks, such as convolutional neural networks, research was emerged for the use of the deep learning models to detect glaucoma in medical images. The convolutional neural network is a deep learning model used for image classification. The model learns from the dataset, extracting the necessary features to make its classification. But there is a concern about the fact that convolutional neural networks are not very transparent in their operation, not bring explanation about how they arrive at the prediction. For this reason, interpretability techniques can be applied to the model to bring a better understanding of how it works. Based on this work has as objective apply two interpretability techniques in a convolutional neural network for the glaucoma detection. Here we have a flowchart of the steps taken in this work. The first part was the preprocessing, where the images are preprocessed before they enter for training. The preprocessing done in this work is just a resize of the image to the size of the input layer of the network. In addition, in this step, some images that are considered noisy are deleted from the dataset. After that, the next step was the implementation of the architecture of the convolutional neural network. For this work, the ResNet50 architecture model was chosen. After training, the evaluation was based on the accuracy value. After the model presents a good result, it is saved for the application of the interpretability, which is the last part of this work. Among the types of interpretability, the interpretability technique chosen for this work was the one that brings pixel attribution. The pixel attribution technique presents a visual response of which parts are most important for the convolutional neural network make the classification. Two metrics were used here, the LRP and the gradical. Both have the same objective, which is, for a training model and the input image, it can execute and bring a heat map, which are the most important part for classification of the image. Difference between the two techniques, it is the way of the pixel attribution is calculated. While the LRP goes to the input layer, the gradical goes only to the last convolutional layer. For this work, the databases used were Acroman and Rewan. With are two public databases of Fundus images focused on the optical distal area. In addition, a third database was made that joined Acroman and Rewan images, making a greater number of images. The number of images in any database after preprocessing is shown in the table. Before the training, it was necessary to balance the number of images in each database. That's because some databases contain more images of one class than another. All the implementation part was done in Python language. The language was chosen for providing libraries that help in the implementation. For the implementation of the architecture, the Keras library was used. The ResNet50 architecture used was pre-trained with the ImageNet database. Three models were generated, each one trained with a different database and different hyperparameters. Model A was trained with Acroma base, Model B with the Ring 1 base, and Model C with the base that is the combination of the two others. Training was done on GPU, and this has helped to reduce the processing time. To apply interpretability, two libraries were used, Investigative and Catavis. Both techniques were applied to the training models. The results obtained in the training and validation part are presented in this table. The division made in the database was 70% of the images for training and 30% for validation. We can see that the model performed information when validated against the same database they are trained on, but they work badly when tested with a different database, which led us to understand that although the images are similar, there is a difference for the network to the point of not being able to make the correct classification. The models involved are chosen for the application of the interpretability techniques. Here, we have the LRP and Glaucoma results applied to each trained model, where the images belong to the glaucoma class. For each model, the technique was applied to the image on which the model was trained. The parts in red indicated the most important areas for classification. The more red, the more important that the pixel was for the classification. With the interpretability, we can see that the LRP brings more punctual results than the graphical. This is happening because the way the importance was calculated. But we can conclude that although the techniques were different, they point to the same area of the importance in all models. What is the area of the optical disc? That it goes along with the medical papers that say that the are most important areas for the glaucoma diagnosis. Early diagnosis of glaucoma is important to prevent the disease from reaching the most serious stage. With this work, we saw that convolutional neural networks have a promising performance for classification of fundus images, and may be a technique that will help in the diagnosis of the disease in the future. The combination with interpretability techniques can bring a more confidence to the model and a better understanding of the most important areas for classification. For future work, it would be an investigation in the preprocessing of images and see if it would affect the validation of the model in dataset on which it was not trained, in addition to apply the system to the other datasets. Another point would be to take the interpretability results to specialize in their area in order to better understand the results and analyze how it could help the diagnostic. Here are the references used in this work. Thank you.